Okay, good afternoon. Before I start, 那个待会结束，楼上5楼有餐会，那就欢迎大家去参加餐会，然后聊聊天，好吗？ Okay, today, lecture 3, we're going to go through all the detail, how to compute persistent diagram, persistent homology, hands-on experience, okay? So let me remind you what is the persistent homology. All right, so this is what exactly we're going to do today. So from last time, we learned a little bit about persistent homology, right? You have homology group, and now you create a filtration, and from the filtration, you will be able to compute the persistent homology, okay? So let me give you one simple example to remind you, to summarize what we have so far, right? Suppose you are given by this 3x3 images, right? Very simple images. And the corresponding pixel value or intensity value is on there, 111, 222, 310, 3, right? So we're going to go through the sub-level set process or the filtration process. So when threshold value equal to 1, you fill in the left column, and that's the first place you create a topological feature, one component. And when t equal to 2, you create another component, okay? And when t equal to 3, you can now see it forms a one connected component and also a one-dimensional whole, right? So the Beatty number becomes 1, 1 at that point. And you can see from threshold value from 3 to 9, this whole persists, well, lives for this long period of time. And when t equal to 10, when you fill in the last whole, everything becomes one component, and then you stop the filtration, correct? And we learned about, this is the entire process of the persistent homology, and you can view the persistent homology in terms of the persistent diagrams. So this is a two-dimensional image, so you're going to have a zero-dimensional persistent diagram, you're going to have a first-level persistent diagram. And the zeroth level is the information for the connected components. The first level is for the one-dimensional whole. And now you can see there are one infinite generator that's marked as the red, and this is blue dot is right here, 2, 3, born at 2 and die at 3, and there is a one-dimensional whole born at 3 and dies at 10. So this is what we have so far. Any question? Okay, good. Okay. So this is what we're going to calculate today. So we are going to give some images, and then we are going to compute the persistent diagrams. Okay? All right. So let me give you some overview of the software so far. Right? This paper is in December 2017. Right? So this paper summarizes almost all the persistent homology packages. Okay? The roadmap for computation of persistent homology. So here is a list. Right? Those are the popular list. Okay, so let me just go a little bit. Okay. So the first one is called Java Plaques. This is developed by a group of people in Colorado State University, I believe. And as the name suggests, this code is implemented in Java. So if you are familiar with Java, maybe you can do that. And there's another one called Dinosaurs. And this is one of the earliest software, and it is developed by the group of people in the West Coast, in the Stanford people. So They are written in C++, and apparently, if I remember correctly, yeah, that's right. They have a Python API, so you can, if you're familiar with Python, that might be the one you can try. So here's the trick. Which one should you do? Usually it's really the personal taste. If you know one, then the other will be very, very similar, right? Just know the data format, then everything else will be very, very similar, okay? And here's some more DIFA. This is getting more popular, and I personally like this one better, okay? Because this code utilizes the parallel computing. Right? So if you have a multi-core or GPU, well, I don't think they support GPU, they support multi-core. So you have many CPUs, this take advantage of the parallel computing. So this can be fast. But again, this is written in C++, so you will have to compile. All right. And this is called a Ripster. This is currently the best software you can find so far. It's like 40 times faster than any others, but it has one drawback. It can only do one particular complex. Right? So far we talk about if you have point cloud data, you have image data. This is specially for the point cloud data. If you have a point cloud data, Ripster is your friend. Okay? Excuse me. All right. And today, the software we're going to use today is called Perseus. This is written in C++, but it has a very user-friendly API, so we're going to use this for today's lecture, okay? And it's very easy to use. You can download the Windows version. You have Mac version and Linux version, very easy to use, but it is not the best performance out there, right? Just keep in mind. Okay, so I hope you have the computer ready. So we're going to download this package, Perseus. Okay. So what you do is you first go to Perseus. You type Perseus homology, and there should be the first one, Perseus persistent homology software. You click it. Okay. And you can click on the download page, and it is a compiled version, so you can download the Mac, you can download the Linux, or you can download the Windows. Okay, depend on your machine. So I'm running on Mac, so I'm going to download the Mac, and this is an executable file, so you don't have to worry about how to compile, just execute, okay? All right, slow me down if you can follow me. All right, next, what I want you to do is go to my web page, which is where is my web? Here. Go to my website, www.sitegoogle.com/yu-minchung, and I prepare some file for you to download. Right, so if you click on teaching, slow going down for NCTS, you click on this, there are files you can download, and we're going to use this file today.
Can you write down the address?
The website?
Yes.
Okay. Let me show you the easiest way. You type my name and type UNCG layer, you should find it. This will work too. www.uncg.edu/YCHUNG2. Make it larger. Either one is fine. 打过. Good. Okay. Any questions at this point? No? Okay. All right, so when you click on that link, you should see the file I prepared for this time. So you can download everything in one folder if you want. Okay. So it has some test images for you to play, and there are some script files we're going to use. Oh yeah, teaching. Go teaching and go to very bottom of the teaching page. There's a small icon for NCTS. And then this is what you should see. The file. Good. Any questions? So you download this folder and put Perseus in this folder. So then you will be all set. You can see there is a Perseus, but this only works for Mac because that's coming from a MacBook. So you're gonna replace this Perseus by the file you download from the Perseus website. Okay? That's all you need to do. Okay. Doing okay over here? Oops. Doing okay over here?
Yes.
Okay, okay. Okay. So the next step, I want you to open MATLAB and then go to the folder where you download all the files. So it's currently in this folder. So you download everything. Okay, good. So I can make, let me make this larger preference. Don't know. Can't. All right. Everybody is ready? Is everybody ready? All right. The first thing you can try is you can try to do system. Okay. Before I do anything, you can go to the Perseus. Where is Perseus? Yes. Okay. So we're going to use for the cubical complexes, right? So that's we're going to implement the images. Right? So we have a lot of images. So here is the data format, and it's very universal throughout the software. Every software has a very similar input file. Okay. So the software you download is actually just a one file, one executable file, compiled from C++, whatever. So it's just one compiled executable file. So it takes in an input, so you're going to prepare your cubical complex, okay? So in this cubical complex, this is the format of the data, right? You're going to feed in an input file, and in that file, the first entry is the dimension of the cube. So we have an image, two-dimensional image, then this is going to be 2, and followed by row by column. So what is the size of your image? So in my case, in this toy example, the case will be 3 by 4. In the toy example, in my slide, we're talking about 3 by 3 image, then this will be 3 by 3, okay? And followed by one-dimensional version of that image data, right? Okay? So this will be the burst time of the 2D cube at 0, 0. Right? So it's going column-wise way. Right? So you have a two-dimensional image, and it will transform to a one-dimensional array. That's how Process reads the input file. Okay? Very good. Very good. So here's what happened. All right. Here's what happened. If you click on Run Process, I already write a script to implement all the small things. I don't know how to make this larger. Can you see it? Anyway. From the file you download, this file called Run Process. So this is a script I wrote, a very simple script. It just takes in an input of a matrix, and output will be the data format needed for Process. That's all this file does. All right, so you can see this is taking an image, followed by the size of the image, and this vect is really coming from the reshaped size of the original image. Right? So it should be fairly straightforward. And then to execute the process, this is the command. Execute process, specify this is a cubical complex, in other words, image data, input file, and this is the output file. So I said input file equal to output file. That's just the convention. Cool? Okay. So let's play with this. So let's do a very simple example. This is the toy example we did in class. Oops. All right, let's do this very simple example. Suppose I'm going to have this image, 1, 1, 1, 1, 3, 2, 1, 10, 2, 1, 3, 2. Let's see how I would do. All right, so 1, 3, 2, second row, 1, 10, 2, and 1, 3, 2. Okay? So now A is my image data, very small image data. Questions? Okay, so now I can execute my run process to see what happened. I can do run process. The first input is the file name. It is just user-defined name, whatever. Okay. And the second argument is my actual image, A in this case. And if you hit enter, it will tell you, okay, I'm reading 9 burst time from the input file, and then this is all the computation output from the process. Right? you can ignore, but it is what it is, okay? And now I show you down, you can consult temp star.txt to consult your output, and you can see it's here, temp 0, temp 1, and temp 2. Right? Well, it shouldn't be temp 2, it should be just temp 0 and temp 1. So temp 0 will be the information for 0's homology group, and temp 1 is the first level homology groups. Okay? Is it? Do I go too far? Too fast? Can we follow? Okay. All right. And now what you can do is you can do persdia. This is the way to visualize the persistent diagram. It's included in the file I sent you. Okay. So you can do temp 1, for example, .txt, and then you will see a persistent diagram right here. This is what we saw before. Right? This is a very simple example. This is the first level persistent homology, burst time 3 and death time 10. Just exactly what we see in the slide. Okay. Good. And you can also visualize 0's level. Right. There are 2 of them. One generator born at 2 and dies at 3. And one generator is infinite generator. Okay? So let me pause here, make sure everybody has the same image before I move on. Okay.
没有 work 所以
不能 work. Okay. 你的呢？
我不知道哎，多听。
还有你是 Windows 的，你的 Windows 你下载在哪里？对，你要把这个改成 Windows EXE。这样，对，抱歉了，没关系。Windows 这个 EXE，哎，你再拼一下，应该这样就可以。对。把它改成 WIN 是吗？对，点 DAEXE 哪里搞错？你们这边呢？我有改。
Windows 是点 EXE 吗？
对。
然后把点撇拿掉。
对。
问题是我的 Windows 点哪里？
你是 Linux 吗？
是。
你是 Linux？
还是说我这个？
你是下载 Linux 吗？
我知道为什么。
你可以修改一下你的那个就可以了。好不好？没了。还是下载。OK。Yes。
就说它这个是把它丢到 main 的那 folder 就可以了，是？它这个本身会 run 吗？我有点 confused， 就是它为什么是文字？
它不会 run， 它是一个
直接档，
它是一个
丢到这里面去就可以了，就是它同一个 folder 它就可以找到它这样。所以你这 file
没有，我是在同一个 folder 里面弄的。
就是说你把它放到一个 main 的 folder 里面，
对，
就这个经常就会 run 了，
你要执行它，你要有一个 executable 的指令，它才会动。
对，不是说是像，就是说你直接按它是不会
对，直接按是不会跑。
它是说你要把它放到 main 的 folder 下面，然后它就叫它这样。
对。
我可能也许最后你把这个档案寄给我，我更知道我就可以 run， 就你现在 run 的这个
OK。
自己 run， 因为现在这个我们看你没 run， 他会觉得我在当中干很久。
OK， 没问题 ，No problem。No problem。OK。 right? So I can move further. So now what you can do is we take care of this very simple example. Now let's calculate this image, right? So I'm going to calculate a persistent diagram for this image called parts, okay? P-A-R-T-S. So I'm going to use the command read parts, read. Okay. So I am read, so it will read in an image, right? So this will be a matrix. Okay. So you can visualize this image by I am show. This is the image we are reading in. So this is the image. So now we have this image. We're going to calculate the persistent diagram of this image. Okay? And keep in mind, the data format is a bunch of, it's a matrices, right? So let me just remind you. An image is a matrices, and this is a 128 by 128 matrices. Okay? And now I throw into Perseus and see what happened. So I'm going to run Perseus. Run Perseus. We say parts. Okay. Good. So this is user-defined file. You can do whatever you want. And this is part coming from my image. Okay. And you hit enter. Then this is run. You see, I didn't lie to you. This run real time, so fast. Okay. It's very complicated, but it can run real time. And now you should see the output part 0, part 1, part 2.
So behind it, so behind it, so when you read the image, right, you get the function, right?
Yes,
And
yes.
then you do the persistent on this, the label set of the function.
Exactly.
So it's so, but how? So it's so like it did this automatic, like because how many like say the function price is 0 and 1, right?
Mm-hmm. Well, function is between 1 to 255.
Okay.
This is the grayscale image.
Oh, okay. So it's discrete value.
Yes, it's discrete value.
And
Yes.
then you try to also just use this all and then convert it to the okay.
Yeah. So what behind the scene is actually the Morse theory,
Okay.
but also some matrix analysis. So you,
So they can do it. If you have an image, then you can do this just import and then they'll just do this for you.
say again?
No, I say if you have an image,
Yeah.
then just so it's very simple. Just read this and then do this.
Yeah.
If it's color one, it's okay.
If this is color one, then you may have to do something
You
because
have different dimension.
you have a three-dimensional.
Three function.
Exactly. So you have to maybe do a reduction or maybe transfer to a grayscale image first. And
Oh, I
then
see.
yeah. Very good point. Cool. And now you can also look at the persistent diagrams. Okay. And this is the zeros level persistent diagram for that image. Okay. And you can also use PersDia to plot the first level persistent diagram. Okay. Good. I don't know why they give me a different size, but okay. So you have a zeros level and you have the first level persistent diagram. Okay. Good. And then like we said before, if you look at the original image, if you look at the original image, from our eye, from our very smart eye, you may see there are this is a one-dimensional hole, 2, 3, 4, 5, 6, 7, 8. You may see 8 one-dimensional hole, and you may also see 5 zero-dimensional components, and that's all depicted in the long life generator here. This is the zeros level persistent diagram, and how many long lifespan generator? 1, 2, 3, 4, 5. Right? So that 5 generator related to that zeros component you see. Okay, and here you can count. There are 8 one-dimensional holes. Good. So this is very simple. This is how you can use this code to calculate persistent diagrams. Okay. Any questions at this point? Okay. Now you can close it. Maybe I don't. Okay. Okay, now what you can do is, now we have the file, part 0, part 1, you can actually manipulate with the birth and death coordinates to get more information. So for instance, you can read in the first level persistent homology. Okay, so if I look at this, it's all pair of the number. The first column represents the birth value, second column represents the death value. So now you can do statistical analysis on this persistent diagram, or you can do some data analysis trick on here. Okay, so for instance, you may wondering, how do I look at this one? It looks like a long life generator, right? So maybe you can sort. You can calculate the distance. Okay. Remember what does P? The second column, death coordinate minus the birth coordinate, that tells you the lifespan of that feature, right? The longer the life it is, the more important this feature is, okay? So this is a way you can take a look. Everything else is like 50, below 50, and there are 8 of them, 1, 2, 3, 4, 5, 6, 7, 8. Is very significantly larger than the rest. So those 8 generator might be the true feature. Okay, so this is very simple, just to illustrate what's happening there and how you can manipulate with this data. Okay. Any questions? Good. Let's move on. Okay, let's move on. Excuse me. All right. Let's go back in this persistent diagram one more time. There's so many information you can do, right? And one of the most important, well, one of the most fundamental one is, well, how do I recover the Beatty number from the persistent diagram? Okay, if I just only care about the Beatty number at a certain threshold, for instance, what is the threshold? What is the Beatty number at the threshold value 60? Right. You may want to know that. So from the persistent diagram, how do we do that? Okay. Well, luckily, it is defined to be, I hope you recall, this is what we do last time. The actual Beatty number at certain threshold, let me do this, is equal to the number of points in the following set. Right? B burst value. This is a persistent diagram. Burst value less than equal to t, and the depth value greater than t. This is the fundamental lemma in persistent homology. Okay. This is how you can relate it back to the original Betti number. Okay? And I have this very simple code written for you. This will capture this guy here. Okay? Good. So go back to the question. Maybe I want to know what is the Betti number at the threshold value 60. So what is the Betti number at the threshold value 60? Okay. And here's what you can do. You can do this PDT equal to get PDT PD1 60, right? 60 is my threshold value, okay? And the PD1 is what we captured before. This is the first level persistent diagram from the parts. Okay? And then the Betti number is simply the number of generator. So you just do the length, NCTS, PDT. So I will tell you there are 297 for beta 1. Cool? Good. You can also calculate this. You can also calculate this. NCTS. Right, 300. Right, so the Betti number at threshold value 60 will be 300 and I forgot the other one. 300 and 297. Cool? That's how you can recover the Betti number from the persistent diagram. Okay? Cool? Any questions? Okay, good. Good? Okay. And now, just to make sure we are all on the same page, that Betti number, you can act, that's exactly this thing I'm doing it here. Oops. I remember. So this red, pink box is exactly this set here. Right? So the Betti number is going to be the number in this box. So in this case, there are only 5 blue points, well, 5 points in this box, so Betti number is 5. There are 16 points in this box, so the Betti number is 16. Okay? Good? So let's do a very small one. Right, something like that. So if you have at threshold value 90, there are 532 holes because there are how many points in that box? Okay, that's here. Okay. Good. All right. And the next thing I'm going to show you is the stability results. Right. So we talk about the stability. The distance, if you have 2 functions, f and g, they just vary a little bit, right? And their persistent diagram will be also a little bit different. Okay, so it's governed by this famous result. So let's take a look at this, how to see it in practice. Okay. So the code I'm going to use, if you have a Mac, you can do it easily. If you have a Windows, you may have to do something. So the code I'm going to use is called HERA. Okay. So this is the state of art, the most efficient bottleneck distance code so far in the world. Okay, so it can calculate the bottleneck distance. It can also calculate the Boston-Times distance. So if you want, this is going to be the most efficient so far you can find. So you can download this and just make CMake and compile the file. You will be able to run this code. Okay. All right. So to demonstrate to you, this is what I'm going to do. Okay, so now I have the part, PRTS. Right, this is my original image, correct? And now suppose I'm adding some noise. Right? Maybe I'm adding some noise version part. I am noise. Okay, so I just add some additive noise to my original image and see what happened. If I look at the I am show noise part, that looks like this. Okay, it's more noisy than before. See if I can do a side-by-side comparison. Cool. I lost track. Oh, there you go. Right. So it looks like, well, I'm not sure. Yeah, it looks like this is more noisy than this one. Okay. This is the noisy version of this one. And now I calculate a persistent diagram to see what happened. Now I can do this. I calculate a persistent diagram, noise part, noise part. Okay. And it's very fast too. So let's look at the persistent diagram of the noisy part. Okay, it looks like this, right? Really crazy. Okay. If I look at the original persistent diagram, what does that look like? Part. Okay, let's look like this. Too many. Okay. Good. So you can see it looks like this hump is going to get amplified, right? It's become brighter. It's becomes brighter. Okay. Good. And overall, then now you can calculate the distance between those two persistent diagrams. And the distance is going to be bounded above by the original noise. Okay. So, oops, sorry. You can calculate the distance. Okay. I have my bottleneck distance code here, right? If you like, I can help you install or compile this, but this is coming from that website, and you compile on your machine, and you will obtain this executable file. And this is here, I'm just executing this file. This function takes in two persistent files. This is a persistent diagram. This is another persistent diagram. And if you calculate this one, okay, so the distance will be 48. Okay, so the distance between that two persistent diagram is 48. Okay. All right. And I hope I convince you this really is in real time. Right? This is can be done efficiently, even though the distance formula looks very, very complicated. But there is a way to do it. Okay, good. And before this code, like you said, it's very, very difficult to do the distance computation. I have a really old code. For this size, it will take like 30, 50 minutes to complete, but this can be done really fast. So, okay, good. Any questions? Oh yeah, I have not finished yet. So you can also, to convince you, right? So if I calculate the maximum distance between the noisy part and the original part, this is gonna be, the maximum is 92, right? So this is below this guy. Right? So that's exactly the stability theorem statement. Okay? So a small perturbation on the function, there will be a small perturbation on the original or on the persistent diagram. And this is how you can do it. Good? Okay. Very good. All right. And the next thing I'm going to talk is two more things. So I'm going to show you one application. Okay. And after this, I believe you can all do it. Okay, I'm going to talk about this texture classification, which I believe you all have the ability to do so. But here we go. This is a texture classification, right? So we have 25 different textures. You have a pasta, you have tile, you have form, you have chips, you have fur, a lot of textures. And the goal is to classify those different textures, all right? So you are given by a bunch of image in this texture, you're given by a bunch of image in this texture, and you're going to do supervised or unsupervised learning to classify those images. And this is a work done by my graduate student, Austin Lawson at UNCG. So the data set we're looking at is called OUTTEC. OUTTEC is data set from University of Oulu in Finland. So they have this image taken in a controlled way. This is the texture there, and this is the machine in a fixed angle, in a fixed resolution, so you all have the same quality of the image. So that's good. So there are 15 different test suites, and there are digital grayscale image for the textures. If you're interested, you can download. It's for the benchmark purpose. So the data set we're looking at is suite 0. It contains 48 images of 24 different textures. And another different test suite we're looking at is 48 image and then 3,000 test images. Okay? So those are something you can play with. Okay, so the thing we're going to do is called the Euler characteristic curve, right? So I hope you keep this in mind. What is Euler characteristic curve? Well, what is Euler characteristic? I think many of you know. Euler characteristics is really alternating sum of the beta number, beta 0 minus beta 1 plus or minus beta 2, and so on and so forth. Okay? But what about the curve? Right? So the curve really means if you have the threshold value, just like before, if you have the threshold value from 0 to 1, for each threshold value, you can calculate an Euler characteristic curve. You calculate for every possible threshold value. That's how you can get the Euler characteristic curve. And this has been studied in the field called random geometry field. And it has application in the physics. Okay, so it's a very nice, beautiful, and simple stuff, Euler characteristic curve. Okay, and before the persistent homology, there was a people in Israel. They discovered that Euler characteristic can somehow do classification, to do classifier. Okay? They are not necessarily doing the image, they're doing something else, but the idea is very cool. They use the Euler characteristic curve, they were able to distinguish between a Michael, horse, cat, and dog. Okay. So we're using a very similar idea. Right, we have a different textures. This is a texture number 1, 2, 3, and 4. Right? Like before, for each one, you can calculate the Euler characteristics, right, from the persistent diagram or from other way. But here, we using the persistent homology. First thing we do, we calculate the persistent homology, and then we can calculate the Euler characteristics. And this is one of the examples we found. For this type of texture, it looks like this. For this type of texture, it looks like this. So we were somehow able to classify those images. And my students take a step further because we didn't take full advantage of the persistent diagrams. So what happened here is we're only taking the number of set in this set, right? And you disregard a lot of information. So for instance, let me maybe show you one example that might be easy. For instance, this is the rectangular box, right? And the Beatty number don't care. Just count total number here, right? So that's why we said we don't take full advantage of the persistent diagram, because you have additional information. You may have the lifespan information in this box. You may also have the location information in this box. Perhaps those 5 is more important than those, or perhaps those somehow tell you the signature of some texture, right? So you can do more. You can do more things in this box, and that's exactly what my student is doing. He generalized this Euler characteristic idea to what he calls persistent curves. Okay. This is the alternating sum, which is very simple, and this is the counting measure. You can do G, right? So if G is just a constant 1, then you recover the Euler characteristics. And here is what really the point we're trying to make. You can really do a lot of different functions here, some meaningful function from the persistent diagram. For instance, you can do the lifespan. The G can be the birth coordinate minus the death coordinate. That will give you a different information. Okay. And this is the result we see. Okay. from the benchmark, the best result that's submitted to their website is called Garber filtering. And if you're familiar with the Garber filtering, you will know this is a way to do rotation and spectrum. All right, so if essentially you try to get the information from the textures, okay? And it's get 99.5%. And then keep in mind that in that Gilbert filter, you're gonna have a lot of parameter to tune. And I wanna make a point before I make into here. If we just do the plain ECC, plain Euler characteristic, it will give us like 95% accuracy. What does that mean? Well, that means somehow it's worth studying what is ECC might be the review some important characteristic of each textures. Because think about ECC. ECC is very plain simple. It's just beta 0 minus beta 1. There's no parameters involved. But somehow it can help you get this high score. Okay? So maybe it worth study, you can study each one texture. Perhaps ECC is the best, well not the best, somehow tell you about the topology of the image or topology of the texture. That might be helpful. And then my student also trick a little bit doing some persistent curve. I think the best he can do is like the weighted Euler characteristics. So instead of constant, he's adding a different weight on the Euler characteristics, and he was able to get a little bit better, 96%. Okay, slightly better than ECC. Good. Cool. So I think at the end of this class, I hope you all, one thing to mention, there's another method called kernel TDA. They obtain the results like 70%. Okay, good. Okay, any other questions? No. Right. Okay, so if you go to my website one more time, where is my website? Okay. I include a different texture data set called UIUC texture. Okay. Similar, but this data set has higher image quality. So if you want to play the same game, I think you can do it. Right? This UIUC texture data set, you will be able to find some characteristics and then maybe classify the images. Okay. You can do that. Any questions? Okay. Right. The last example I want to show you is the point cloud data.
So can you combine this with like machine learning?
Yes. Yeah. That's the goal here. Yes.
Okay.
Yes.
Well, when you write SVM, is a support vector machine?
That's exactly right.
It's already somebody's
Yeah.
And I guess because data set is not really huge, neural networks are not really applicable because support vector machines are kind of the best for medium or small size data sets.
Yeah. Exactly.
You don't need a deep learning.
Well, deep learning could not work here. That data set is
Small,
not-
right?
it's
Too small. Yeah.
small.
The image, the size will be too small. Yeah. Very good point.
Like if you work at a medical image, would that be, or it's similar? I mean,
Yeah. If you work on medical image, that will be a very challenging problem.
also, you hear most of the information is like 2 dimensional, right?
Yeah. Exactly.
Because so can you, the problem is when you have medical image, even it's coming from, say you have from a lung, right?
Mm-hmm.
But the image only is 2 dimensional. But can you do 3 dimensional?
Reconstruction.
Because if it's something like otherwise your beta 3 will be 0 because it's coming from image. So
Yes. Yes.
are there people doing this? Like so.
So some people will do the scan, right? So the
So you get 3D information.
you got the 3D
Okay.
information.
Then you can do this.
Yeah. But more people, okay. The next thing I want to show you is the point cloud, right? The point cloud, right? So this is not image anymore. You want to think about something else. So this could be some other data, the point cloud data. So we want to understand the shape of this data, right? So to do it, you grow the ball around the neighborhood of the point, and you keep growing the ball. You essentially looks like, oh, this data looks like a donut or a circle. Okay, so that's what idea is very, very simple, right? And this is type of data I mentioned in the beginning. It's if you have the data like this, the best thing you can do is Ripster. Okay, Ripster can do this super fast. Okay, but Perseus can do it too. So we will demonstrate Perseus just for educational purpose. Okay, do this, and then that's this. Okay, so if you look at, I have written a code for you guys called a get sample circle test. Right? Suppose I have a point drawn from a circle, okay, and we will calculate the persistent diagram of that circle. So here's what happened. Get sample. Right. So this is the data we are looking at. Suppose I have this point cloud data. Right. And then you don't know what it looks like, just some point cloud. And you can use topology, persistent homology, to help you understand the shape of this data. Okay? Okay, good. So you can run Perseus rips one circle. Okay. Now I hope I'm using a different file because I'm going to use a different options in Perseus. Okay, so this is options called rips. Sorry, one more time. So it is still under Perseus. Perseus can handle the rips complex as well. So this is called the rips complex. Okay. It's calculated in Perseus. There are 100 points, and that exactly is doing that. Grow the ball, and then see what topology is.
So the other program will extend the point to
Yeah.
the ball that you mentioned last time and become a complex.
Yeah.
That's just point, right?
Yes. So they have the. Yes. So what happened is you grow the ball. If the ball intersect, then you view those two as the
So in
one
this
component.
program, you need to set a parameter, say how large you want to grow the ball.
Yes. In Perseus, yes, you do.
So you set by yourself.
Yes. Yes. Very good question. But in Ripster, you don't have to do anything. Ripster will take care of everything. Yes. So as Professor Trey mentioned, this is the file I wrote. But if you look at the Perseus, you have to specify the step size and the number of steps. So in this case, each time the ball grows 0.01, and then I iterate 1,000 times. That's the code. Okay.
But before you see the data, how do you set up this parameter? Like, or you do some experiment and you sort of try to
Yes.
see the picture.
Yes. Yes. Well, that's again. This is really the limitation of Perseus because
Okay.
Perseus is really good for the imaging, for the
For the point cloud, you need to do some deep processing.
Well, for the point cloud, you're better off using Ripster. Yeah. So for Ripster, you don't have to specify those parameters. It will detect for you. Yeah. So we can take a look. Ribs. Okay. Right? So you can see there is a one-dimensional hole lives for a very long period of time. So it looks like this data is really drawn from a circle. Okay. Again, the thing I show you here is really for you to understand what happened in persistent homology. But in reality, when you see a persistent diagram, you really have some knowledge about your data and some knowledge about persistent homology in order to draw conclusion. Okay? Cool. Any questions? Okay. If not, I think this is all I want to say today, and I will stay here, help you set up your computer, help you run the experiments if you want. Okay. Otherwise, thank you very much. Oh, I forgot. Wednesday, the last lecture, I'm going to talk about applications. Right. So I will talk about some reasonable application in this field. Okay. So we are really coming. First lecture we talk about theory. Second lecture we talk about a little bit theory and then talk a little bit about data. In the third lecture we talk about the tutorial and the data. And the last lecture we will talk about the application. Right? Everything will be data analysis. Okay. Okay. Thank you very much, and I will see you next time.